So let's look at this idea of resistant motion. And essentially, because we're talking about straight line motion, there's really only three scenarios that we're going to talk about. So resistance, as we know, is always opposite direction to motion. That's Newton's third law. So we could be moving in a horizontal line if we break it up, the horizontal component. So essentially, if I say, well, my resultant force is going to the right, the actual forces on it, I just have resistance going in the opposite direction, and we'd end up with something like that. Our resultant force is equal to negative whatever the resistance is. We could divide through by the mass and get an acceleration equation. But when we resolve it into our vertical component, it might be going up, and so resultant force I'm saying is going up. We'd have the force due to gravity going down, but we'd also have some form of resistance going down as well. And we'd end up with this sort of equation. Again, divide through by m, and then play around with the calculus. Now, our basic ideas don't change just because there's resistance. I mean, the greatest height is still going to happen when velocity equals 0 and things like that. That's not going to change. The third case, which would be different to the up case because of the direction of resistance, if I define the resultant to be down now because I'm moving down, the force due to gravity is going down, resistance is now going up, which means the equation will change slightly. Because I've defined the direction that I'm moving to be positive, the force due to gravity is now positive instead of negative. That's really the only difference. We still end up with some sort of equation like that. When we talk about downward motion, there is this thing called terminal velocity. And terminal velocity, I guess the simplest way of thinking about it is when the acceleration is equal to 0. Like the forces balance, I guess, is what we're saying. So the resultant force would be 0. Let's have a look at some questions. Some 2020 paper. We've got that box being pulled along the ground at some angle there of 30 degrees, but also has some resistive force, which I guess would be friction, acting on it. We want to find R. Now, R in this case is actually that normal contact force. So they called it R. Okay, so if I just look at the vertical forces, which means this one going off at an angle I need to resolve into horizontal and vertical, and so going down would be 50G, going up is the force I'm trying to find, that contact force, but also we've got this force of 200, and it would be sine 30 because it's opposite the 30 degrees there. But we know that box, it's not like it's jumping up off the ground. So those forces must balance. So I know overall the resultant force, the vertical forces, must equal 0. R plus 200 sine 30 minus the 50G must equal 0, which allows me now to find R. They must have said take G as 10, did they? Now they want us to look at the horizontal forces and show that the resultant force, they've called it the net force, but the resultant force is approximately 53.2. I'm pushing it to the right, so that's where I'll define my resultant force. Remember, that's not actually a force in it, it's the result of all of them. To the right I've got 200 cos 30, and I've got the resistive force, which I guess is friction. And remember we talked about that, we said friction usually is some multiple of the normal force, and that's what they're saying here, it's 0.3 of R. Yeah, so net force is just another way of saying resultant force, really. I won't bother dividing through by mass because they've asked me to show the force. That's just a matter of substituting in, and we get 53.2 newtons. So what's the velocity of the box after the first 3 seconds? Okay, well, we've just said that resultant force horizontally is 53.2. Now I'll divide through by the mass and get an acceleration, and because I want to link velocity and time, I'll use dv to t for acceleration, and so it'd just be 53.2 over 50. I hate decimals and fractions, so I've made that 133 on 125. Separate out the variables, and it just becomes, oh well, that's nice, because it's just the integral of the t. That's a simple little one there, 133 on 125 times 3, so 3.2 meters per second. Particle is projected upwards and it's got some sort of resistance, so it's in a resisting medium. Assuming that the retardation due to this resistance, retardation is a force, is equal to kV squared. My resultant force, I'm defining that to be up. The actual forces in the problem, I got the force due to gravity going down, but I also had this resistive force of retardation, kV squared, going down. They were my initial conditions, x equals 0, v equals u. I can create my equation of motion there. There it is. Acceleration is minus g minus kv squared on m. There's two things we have to do here. Find the greatest height and the time taken to reach that height. Find the greatest height, I'll use v to v dx because I want to link velocity and displacement together, because greatest height will occur when velocity is 0. Yeah, let's divide through by v, separate out our variables. Could have done that all in one hit, I suppose. Sub in the initial conditions they gave me when x equals 0, velocity was u. There's the answer, but of course I've got to work out the integral, what that actual value is. That's a log function. There we go. Now, you'll notice I didn't worry about the absolute value signs there because, well, mg plus kv squared, it's got to be a positive number. So it doesn't really matter if I have absolute value there or not. And there's the expression. M on 2k, the log of 1 plus ku squared on mg. But they also asked me to find the time taken. So now I've got to link time into it. Well, this time I'll use v to t for acceleration then. But again, separate out the variables. We have a different integral to solve. End up when we integrate m on k root k on mg inverse tan of root k on mg v. Sub in u, sub in 0 with inverse tan of 0, 0. And we have an expression for the time it takes to reach our greatest height. Well, let's do one where we're going down. Body of mass 5 kilos is dropped from a height at which the gravitational acceleration is g. Assuming air resistance is proportional to speed, and that constant of proportion being 1 on 8. Velocity after time t. So we're going down. I'm going to define down my resultant force. Well, they told me it was 5 kilograms, so I said instead of mx double dot, I've said 5x double dot. The force due to gravity will be 5g. Resistance is 1/8 of v. We've got an expression for acceleration. We're linking velocity and time together, so we'll use v to t, and let's do our integration. Separate out those variables. What do we got? It's a log function, isn't it? So we get the log of 40g over 40g minus v. Well, 40 times it. But that's an expression for t in terms of v. We want an expression for v in terms of t, so we now have to make v the subject of all that. Exponentialize, flip both sides. I've got v on the top of the fraction, and there we go. v equals 40g, 1 minus e to the power of minus t on 40. The terminal velocity, I said, well, basically the idea is acceleration equals 0. So I solved that. That comes out nice and quick. Going back to the acceleration formula we worked out, it's 40g. Because there's another way of thinking about it now that we have this velocity time equation. Because what terminal velocity is, I guess, is the limiting velocity. That's another word for it. The limiting velocity. So what's the limit of that as t approaches infinity? Well, we know that exponential part's going to approach 0, so we get 40g. So that's another way we could find the terminal velocity. How far has it fallen? Well, now that I've got an expression for velocity, I'll link displacement and time together. So dx to t. Again, separate out our variables. Subbing into this one, ooh, what a lovely expression. There's an expression for the distance that has fallen. 40gt plus 1,600 ge to the minus t on 40 minus 1,600 g. Some HSC questions there. 2020 had one of these pulley questions. Two masses, logically I guess, yes, the 4 kilo mass is going down because it's heavier than the 2, so you would think, oh yeah, that's the one that's going to move down. And they've given us that the force due to air resistance is kV. What do we have to do? Show that v to t is this expression. Okay, I've got two separate masses, so I work on them separately and then find a way of linking the two together. So on the left-hand mass, we have the force due to gravity, 2 mg. We also have that resistive force, because remember the 2 kilogram mass will be going up. So therefore the resistive force is going down, and tension in that string is going up as well. So the resultant of all that up is positive, T minus 2 mg minus kV. Let's have a look at the other mass. Also has a force due to gravity, but resistance for this one will be going up, and tension will also be going up. There's an expression for the 4 kilogram mass. And we want to link the two together to get this dV to T expression, but we'll notice there's no mention of tension in that. So that's going to be what links these two problems together. I'm going to eliminate the T, if you like. We've basically got a set of parametric equations. So we eliminate the parameter. So I could make T the subject on the left-hand side, sub that into the right-hand side, and then eventually, playing around with that, we get that acceleration is mg minus kv on 3m, but of course acceleration is dV to T. We have our answer. Given that V is less than gm on k, show that when time is 3m on k log 2, the velocity of the mass will be gm on 2k, or the larger mass. There's my acceleration, V to T. Again, separate out the variables. Bit of integration to do. Because they told me velocity is less than gm on k, I actually didn't really need the absolute value signs, because that forces mg minus kv to be positive. And I guess that's why they gave us that information. So we know, oh yeah, that's going to be a positive number. But anyway, I've left it in there. It doesn't really matter. But now I've made that statement. Oh, okay. Now I can say, yes, it is the log of something that's always going to be positive. So mg on mg minus kv is 2. And we get our result that velocity is mg over 2k. 2021. This time our mass is on a slope, inclined at 60 degrees. It's moving down the slope with a velocity of v. We also have our force due to gravity and 2 other forces, both acting up the slope. Show the resultant force is this expression. There's my mass sitting on the slope. I've got the force due to gravity going down. That'll be 5g. They told me that there's a couple of forces, so friction, possibly something else is happening in there as well. 2v plus 2v squared. And of course we have our normal contact force going at right angles to the surface. But they've actually given us the hint there of, hey, go down the slope. That's going to make life easier for ourselves, because then the normal contact force doesn't come into play. We don't have to worry about it. Okay, well that means I'm going to have to resolve forces. That 5g needs to be resolved into down the plane and perpendicular to the plane. Now 60 degrees would end up being there, playing with geometry. So going down the plane opposite the 60, so that's going to be sine 60, so 5g sine 60 minus that resistive force. There's our resultant force. Okay, we need to basically just work out what sine 60 is to get the expression. 5 root 3 on 2g minus 2v minus 2v squared. There's one value of v such the object will slide down the slope at a constant speed. Find this value of v. If it's going at a constant speed, then acceleration must be 0. I just use that relationship we just found and make v the subject. Ooh, okay. Well, is it 2 plus that wonderful expression, or 2 minus? Well, it's going to be the 2 minus, because notice it's over -4, and we know it's going down, and we define that to be the positive direction. So we know we want the positive answer for velocity. Subbing that all in, we get 4.2 meters per second. All right, so 6D and 6E.